Hello, my name is Evan Cardenas, and this is Lab 3 Circuits. For the introduction, the main goal is to know how current and voltage in circuits work with resistors and capacitors, see the electric current and potential difference, find time constant using experimental computed values. The results were the calculated resistance of Y equals 0 ohms, the 47 resistor equals 46.8 ohms, the 100 resistor equals 97.8 ohms, and the ammeter equals 102.5 ohms. The time of charging capacitor roughly equal the time of discharging it. The net V will sum to zero as, it's Kirchhoff's voltage rule, but, we just kind of showed it. And the increasing resistance increases charging and discharging times. Sorry, I forgot to say that at the end. Speaking of Kirchhoff's voltage, here it is. So it's literally just the sum of all voltage drops around a closed loop equals zero. Go figure. Kirchhoff's current rule says the total current entering a junction equals the total current leaving it. Ooh. And the resistor and capacitor relationship is a resistor opposes current flow while a capacitor stores energy in an electric field. And in a DC circuit, for example, the resistor limits current and the capacitor eventually blocks after charging. So part one of experiment, I'm gonna first tell you how we did it. So first we connected the two batteries to each other in a series. Next, we attached a wire to the battery and attached the other end to the 47 ohm resistor, which then had a wire attached to that, which was then attached to the 100 ohm resistor, which had a wire attached to that and was then attached to the negative end of the battery. So yeah, in this case, the system is the circuit. It's the surroundings of everything not in the circuit. The conditions were two 1.5 volt batteries, a 4700 ohm resistor, and two ammeters. And the current, the experimental value was 0.02A. Get this, the actual value, 0.02A. Go figure. Yeah, here's the continuation. This is the graph that we ended up with. From A to B, it is 3 volts. It goes up to 3. From B to C, 0 because it's constant. From C to D, it's negative 0.95 volts. From D to E, it's 0 because it's also just constant. And then E to F, it hits 0, so it's just negative 2.05 volts, and then everything after is 0. So for the resistance, the R47 resistor gives 47.5 ohms. The R100 resistor gives 102 ohms. The R wire gives 0 ohms, and the R ammeter gives 0 ohms. So this is experiment part 2, right? So in this case, we kind of just replaced the capacitor with two batteries. I'm sorry, the resistor with two batteries, and we replaced the capacitor with another capacitor. So. And then we just kind of just redid it. So yeah, the system in this case was a circuit. The surroundings were everything not in the circuit. Go figure. Conditions were a 9-volt battery, 20 and 10 ohm light bulbs, and a 0.2 F capacitor. The procedure, we measured time it took to charge and discharge capacitor, sources of error. I was going with the stopwatch, and I did kind of, I think, mess up the timing even after we redid it. So. Here is the part two continuation of the experiment, part two. So yeah, that's my graph, because it got corrupted, and that's the example. So the time for the R10 bulb charging is 12 seconds. For the R10 bulb discharging, 11 seconds. For the R20 bulb charging, 50 seconds. The R20 bulb discharging, 49.5 seconds. Give or take, it's equal. Round up a little bit. And the slope time is 5.98 seconds. Now the questions. What if you charge a capacitor with no resistor in the circuit? I'll click what our ideal model predict the capacitor to reach full charge. With this prediction happen in real life, you explain. In an ideal circuit with no resistance, a capacitor would charge instantly because the time constant, T equals RC equals 0. Actually, I actually have no clue to say, I'm just saying T. Uh, this would require an infinite current, which is impossible. In reality, there's always some resistance from wires, the battery, and the ammeter, so the capacitor charges very quickly but not instantly. When you measure, the ammeter will show a brief current spike that fades almost immediately. The measured charging time is longer than the ideal prediction because real components and instruments have resistance and limited response speed. Thank you for listening to this, and have a nice day. I forgot this isn't touchscreen, my bad.